The universe is composed of countless mysteries, but at the foundation of everything lies a subtle, elegant truth: the elements. Hydrogen, oxygen, carbon, gold, uranium, each a building block of the cosmos, each with its own story whispered across time. They are the alphabet of matter, the letters from which the universe writes everything we see, touch, and imagine. Yet, for centuries, humanity walked blind among them, feeling their presence but unable to name, classify, or understand them. In the early days of alchemy, the world was a kaleidoscope of substances. Alchemists sought gold, elixirs, and the secrets of transformation. They melted, burned, and combined materials, observing reactions with awe, but misunderstanding their nature. Mercury flowed like liquid silver, sulfur burned with mystical fury, and iron resisted their touch. Alchemy was a dance of observation and imagination, a first step in humanity's journey toward understanding the elements. Though misguided, it reflected a deep curiosity, the desire to unravel nature's hidden language. The unknown of the elements was more than chemical, it was cosmic. Stars forged matter long before humans existed. Hydrogen fused into helium, helium into carbon, carbon into oxygen, the elements that would one day compose planets, oceans, and living beings. Yet, humans could only perceive matter in bulk: lumps of iron, chunks of sulfur, droplets of mercury. The true architecture of nature remained invisible, waiting for minds capable of deciphering the periodic pattern, the order within apparent chaos. In the 17th and 18th centuries, the foundations of modern chemistry emerged. Robert Boyle and Antoine Lavoisier began to distinguish elements from compounds. Lavoisier, with his meticulous experiments, showed that matter could neither be created nor destroyed, only transformed. He named oxygen and hydrogen, recognizing that water was a compound, not a fundamental element. This was humanity's first glimpse behind the veil, the realization that nature had rules, and elements were the atoms of a grand cosmic alphabet. Yet the unknown stretched far beyond these early discoveries. Why were some elements similar in behavior? Why did some combine easily while others remained stubbornly inert? Why did certain elements occur naturally while others seemed almost mythical, existing only in the imagination of chemists or in the fiery hearts of stars? Humanity faced a labyrinth of questions, each element a door leading to both understanding and mystery. The periodic table itself was not yet imagined. Elements were scattered, discovered sporadically across the globe. Gold and silver had been known for millennia. Copper, iron, tin, the materials of civilization, were familiar, but their origins, their relations, and their underlying principles remained hidden. Other elements were elusive. Noble gases, rare earths, and radioactive materials lay undiscovered, waiting for the instruments, intellect, and intuition to reveal them. The unknown was both vast and intimate, encompassing the universe and the smallest atom. Humans interacted with elements constantly, often unaware. Iron forged tools, copper conducted electricity, carbon fueled fire. Mercury and lead poisoned, gold dazzled, and iodine healed. Every discovery carried consequences, yet the true nature of these substances remained elusive. It took a convergence of curiosity, experimentation, and insight to lift the veil, to see not just matter but the story within. Some of the earliest true insights came from patterns and properties. Chemists noticed recurring behaviors. Lithium, sodium, and potassium reacted violently with water. Chlorine, bromine, and iodine shared a bitterness and color. Across these observations, subtle regularities hinted at a deeper order, an invisible architecture of nature. Yet, pattern alone was not enough. The human mind required insight, connection, and imagination to see the elements as a family, as nodes in a web of cosmic logic. The unknown was also a story of human daring. Dmitri Mendeleev, in the 19th century, gazed at his collection of elements and noticed gaps. Unlike a simple list, the elements could be arranged in order of atomic weight, revealing a repeating pattern, a periodicity. Some spaces remained empty, representing elements not yet discovered. Mendeleev predicted their properties, e.k.a. silicon, e.k.a. aluminium. His insight was staggering. The unknown could be anticipated, even quantified. Nature, it seemed, had a grammar, and the periodic table was its syntax. Meanwhile, across the oceans and continents, other minds pursued the unseen. Marie Curie explored the shadows of radioactivity, isolating polonium and radium from pitchblende. Her work revealed elements that glowed with hidden energy, atoms vibrating with force beyond comprehension. The unknown was no longer merely chemical. It was energetic, radioactive, and profoundly mysterious. Nature's building blocks contained within them forces that could illuminate, devastate, or heal. Humanity's relationship with elements was deepening, from observation to interaction, from curiosity to responsibility. The unknown of the periodic table also mirrored the unknown of the universe itself. Each element was forged in stars, in supernovae, in the crucibles of time and pressure. Their stories were cosmic. Hydrogen and helium birthed in the Big Bang, heavier elements in stellar furnaces, rare metals scattered by explosions across the galaxy. To know an element is to know a fragment of the universe's history, to trace the path of matter from cosmic birth to human hands. As we stand in laboratories today, surrounded by beakers, microscopes, and particle accelerators, we are still exploring the unknown. Superheavy elements are synthesized atom by atom, revealing the fringes of matter. Exotic isotopes challenge our understanding, and the search for patterns continues. Yet, even as we expand knowledge, reflection reminds us that every element, discovered or undiscovered, is a story of cosmic forces, human ingenuity, and the quiet poetry of the universe. The unknown is not just absence. It is potential, anticipation, and wonder. It is the mystery that drives discovery, the spark that transforms curiosity into exploration. From the first alchemist's furnace to the particle collider, from gold panning along riverbeds to spectral analysis in observatories, humanity has been drawn to the elements. They are silent witnesses of cosmic history and active participants in the evolution of life, technology, and thought. In contemplating the unknown, we recognize the profound intimacy of the periodic table. Each element is a character, a note in the symphony of matter. Some are familiar and friendly, others rare, dangerous, or dazzling. Each has a story, a birth, a history, and a consequence. To study them is to engage with the universe on its most fundamental level, to trace the narrative of matter from the Big Bang to the present. Thus, Chapter 1 closes on the horizon of discovery. The unknown stretches before humanity like an ocean of possibility, each element a wave waiting to be charted. Curiosity becomes the vessel, experimentation the wind, and imagination the compass. In the chapters that follow, we will witness the experiments that began to illuminate these mysteries, the revelations that reshaped science, the consequences that transformed civilization, and the reflections that connect us emotionally and philosophically to the building blocks of existence. The unknown is the invitation. The periodic table is the map. And humanity, armed with curiosity and courage, steps forward to discover the stories behind the elements. Curiosity alone could not unveil the elements. It required experimentation, the patient, meticulous dialogue between human ingenuity and the natural world. Scientists became explorers, not of lands or seas, but of matter itself, probing, measuring, and coaxing nature to reveal its secrets. They sought patterns and reactions, glimpses of hidden forces, and connections that hinted at a deeper order. Each experiment was a step into the unknown, a conversation with the universe, a dance between observation and imagination. In the early laboratories of the 17th and 18th centuries, chemists began to isolate substances, heating, dissolving, and combining them in search of elemental truth. Mercury flowed like liquid silver, arsenic hid in earth, and sulfur burned with alchemical drama. Experiments were both art and science, careful observation tempered with intuition. Antoine Lavoisier measured precisely, weighing elements before and after reactions, proving that matter was conserved. His balance became a portal to understanding. No longer was matter mystical. It was measurable, consistent, and predictable. Experimentation began to illuminate the hidden architecture of nature. Joseph Priestley and Carl Wilhelm Scheele conducted experiments with gases, revealing oxygen, nitrogen, and other previously invisible elements. They collected, compressed, and ignited, documenting subtle transformations that spoke volumes. Gasometers hissed and bubbled, glassware clinked, and delicate reactions revealed properties that were invisible to the naked eye. The laboratory became a stage for discovery, where human curiosity met nature's cryptic vocabulary, and where elements, long unseen, whispered their identities. Meanwhile, electrochemistry emerged, guided by the vision of Alessandro Volta and Humphrey Davy. With sparks of electricity, they liberated metals from compounds, potassium, sodium, calcium, and magnesium, isolating elements that had never before been observed in pure form. These experiments were dramatic: metal flames, sudden reactions, and brilliant arcs of light. Electricity became a tool to pry open nature's vault, revealing elements that existed in the shadows, hidden within salts and ores, waiting for human insight to uncover them. Experimentation was also spatial, extending across continents and laboratories. Scientists in Paris, London, Stockholm, and Berlin repeated, verified, and refined discoveries. Each experiment was both an act of creation and confirmation, ensuring that knowledge was not anecdotal but universal. Methods evolved: spectroscopy, calorimetry, chemical titration. Instruments became extensions of human senses, detecting properties beyond perception. Through these experiments, elements began to emerge not as isolated curiosities, but as members of a greater, interconnected family. Spectroscopy transformed experimentation in the 19th century. Scientists observed the light emitted by heated elements, noting characteristic lines in the spectrum. Sodium glowed golden, lithium crimson, cesium deep violet. Each element revealed its fingerprint, a signature that could be read from a distance, even in the stars. Experiments shifted from terrestrial labs to telescopes and observatories, linking earthly chemistry with cosmic phenomena. The same elements that glimmered in the laboratory appeared in distant suns, connecting human investigation with universal truth. Experiments were not only chemical, but also nuclear. The late 19th and early 20th centuries revealed the atom's secrets. Marie and Pierre Curie's painstaking isolation of polonium and radium involved grinding, dissolving, and precipitating tons of, or to extract mere milligrams of radioactive elements. Their hands trembled over flasks of pitchblende, eyes alert to every glow and spark. The discoveries of radioactivity, alpha and beta particles, and the transformation of elements under radiation expanded the scope of experimentation. Elements were not static. They were dynamic, energetic, and alive with atomic motion. Isotopes added another layer to the experimental narrative. Frederick Soddy discovered that atoms of the same element could differ in mass, yet share chemical behavior. This subtlety required precise measurement, careful observation, and creative thinking. Experiments with decay, half-life, and atomic mass revealed the richness of elemental identity. Each experiment was a conversation with nature, teasing apart the subtle differences that defined matter, bridging chemistry with physics, observation with understanding. Experiments also embraced synthesis. New elements were crafted in laboratories, atom by atom. Super-heavy elements, existing for milliseconds, were detected through nuclear collisions, particle accelerators, and sensitive instrumentation. These experiments were feats of imagination and precision, confirming theoretical predictions and expanding the boundaries of the periodic table. Humanity was no longer merely discovering what existed. It was creating, extending the universe of matter itself, guided by principles teased from observation and calculation. Experimentation was, above all, iterative. Success was often preceded by failure, as chemists misidentified substances, miscalculated weights, or overlooked properties. Yet each attempt, whether triumphant or flawed, contributed to the mosaic of knowledge. Experimentation was dialogue, a feedback loop between human reasoning and natural response, between hypothesis and result, between curiosity and reality. The laboratory was a crucible of patience, intellect, and wonder. Even simple experiments revealed profound truths. Dissolving salt, igniting magnesium, or precipitating silver chloride became gateways to understanding atomic behavior, bonding, and reactivity. Experimentation made the invisible tangible, converting abstract curiosity into observable consequences. It demonstrated that the universe operates according to principles, that matter is structured, and that patterns can be discerned through careful, creative inquiry. From chemical flasks to particle colliders, experiments unveiled the hidden language of elements. Hydrogen, carbon, oxygen, familiar yet profound, were observed not merely as substances, but as characters in a cosmic story. Each experiment illuminated properties, relationships, and tendencies, revealing the logic of the periodic table. Patterns emerged: periodicity in reactivity, trends in atomic size, and relationships across rows and columns. Experimentation was the bridge between observation and revelation, between the unknown and understanding. And yet, the true power of experimentation lies not only in discovery, but in prediction. Mendeleev's genius was to recognize gaps in known elements, deducing the properties of those yet undiscovered. Experiments confirmed these predictions. Gallium, scandium, germanium emerged, precisely as foretold. This convergence of experiment and theory demonstrated that nature is not arbitrary but patterned, and that careful human inquiry can uncover its laws. The chapter of experimentation closes with a realization: experiments are conversations across time and space. Alchemists, chemists, and modern scientists participate in a continuous dialogue with matter. They measure, observe, and probe, extending human senses and imagination. Through these acts, the unknown becomes partially known, patterns emerge, and elements reveal their stories. Each experiment is a testament to curiosity, patience, and the human drive to understand. Experimentation is the heartbeat of discovery, the hands that touch the invisible, the eyes that see the unseen, and the mind that interprets what is observed. Without it, the periodic table would remain an abstraction. With it, it becomes a living, breathing map of the cosmos, linking human ingenuity to universal truth, matter to meaning, and curiosity to understanding. From countless experiments, failures, and meticulous observations emerged revelation, the moment when the hidden order of elements became visible to human understanding. Revelation is the point where curiosity and diligence meet insight, where chaos transforms into structure, and where the universe speaks its secrets in a language we can begin to read. The periodic table, in its elegant rows and columns, was not merely a list of substances. It was a map of nature's hidden geometry, a reflection of the cosmos itself. Dmitri Mendeleev stands at the center of this revelation. In the 1860s, with a table of known elements and their atomic weights, he noticed patterns, a repeating periodicity of properties. Sodium and potassium, lithium and cesium, shared behaviors, suggesting a law beyond coincidence. Mendeleev's insight was profound. He predicted elements yet to be discovered and even described their properties. Gallium, scandium, and germanium later confirmed his predictions, demonstrating that revelation is not only about discovery, but also about anticipation, a dialogue between the known and the unknown. Revelation also emerged from the study of atomic structure. John Dalton's atomic theory framed elements as indivisible units of matter, atoms combined in fixed ratios, obeying natural law. Later, J.J. Thomson's discovery of the electron revealed internal structure, showing that atoms themselves were not simple, immutable particles, but intricate systems with charged components. The revelation of subatomic architecture connected chemical behavior to physical principles, bridging chemistry and physics and unveiling the hidden dynamics within every element. The early 20th century brought further clarity. Ernest Rutherford's gold foil experiment shattered assumptions of uniform atomic matter. He demonstrated that atoms contained dense, positively charged nuclei, surrounded by electrons in space. This revelation transformed our understanding. The atom was a universe in miniature, with gravity's conceptual sibling, the electromagnetic force, governing structure and motion. Understanding the atom was a revelation not merely of matter, but of the principles orchestrating reality itself. Spectroscopy offered another form of revelation. Observing the unique spectral lines emitted by heated elements, scientists could identify substances light years away. Sodium glowed golden, lithium crimson, cesium deep violet. The cosmos itself became a laboratory. Stars revealed their elemental compositions, confirming that the same atoms found on Earth pervade the universe. Revelation extended beyond our planet, connecting human knowledge to the grand cosmic order and showing that elements were universal messengers, each carrying the story of creation across space and time. Radioactivity, too, offered revelatory insight. Marie and Pierre Curie discovered that atoms could transform, emitting energy in the process. Uranium decayed into radium. Polonium glowed with hidden intensity. Revelation lay in understanding that elements were not static entities but dynamic, evolving participants in cosmic processes. The concept of half-life, decay, and isotopes opened new dimensions. Matter itself was alive with activity, vibrating with forces that humans had only begun to measure and comprehend. Mendeleev's table was revealed not only as classification but also as prediction. When gaps were filled by newly discovered elements, revelation was confirmed. Nature's laws were consistent, rational, and intelligible. Each new element was a victory of human insight over mystery, a confirmation that patterns exist even when unseen, and that patience, observation, and intellect can decode the structure of reality. Revelation, therefore, is both recognition and confirmation, seeing not only what is, but what must be. The discovery of noble gases further refined revelation. Helium, neon, argon, krypton, and xenon occupied a previously unrecognized column of inertness. Their existence explained anomalies in chemical behavior and expanded the periodic table in unforeseen ways. Nature, it seemed, had subtleties beyond even the careful eye of early chemists. The revelation of these elements challenged assumptions, deepened understanding, and demonstrated that the table was not fixed but flexible, capable of growth and refinement as new knowledge emerged. Revelation also came through isotopes and atomic numbers. Frederick Soddy and later Henry Moseley showed that elements are defined not only by chemical behavior but by the number of protons in the nucleus. Atomic number, not weight, became the key organizing principle. This clarified previous inconsistencies and revealed a deeper layer of structure within the periodic table. The revelation was twofold. Chemical properties were visible, measurable, and predictable, and beneath them lay an elegant, quantifiable order, a hidden symmetry in nature. The revelation of synthetic elements extended the table to realms beyond Earth. Scientists created technetium, promethium, and super-heavy elements in particle accelerators, observing fleeting atoms that existed only milliseconds yet conformed to predicted patterns. Revelation now included human creation. The ability to synthesize elements demonstrated not only understanding, but also agency, bridging observation and intervention, discovery and invention. Humanity was no longer merely uncovering nature's secrets, it was co-authoring them. On a philosophical level, revelation transformed humanity's sense of connectedness. Every element is a product of cosmic processes. Stars forge carbon and oxygen, supernovae scatter iron and gold, and gravity orchestrates collisions that spread matter across galaxies. The periodic table is not just a human construct, but a mirror of cosmic order, a reflection of processes spanning billions of years. Revelation, in this sense, is the recognition that we are participants in a universe governed by laws, yet capable of perceiving and understanding those laws. Reflection on revelation reveals its emotional resonance. The awe of seeing order in apparent chaos, of predicting unseen elements, of connecting laboratory chemistry to starlight billions of years old. These are moments where intellect meets wonder. Revelation is not merely cognitive, it is emotional, aesthetic, and philosophical. It evokes humility, joy, and reverence, showing that knowledge is inseparable from the human experience of awe and curiosity. The chemical properties themselves tell stories. Sodium's violent reaction with water, mercury's liquid sheen, iodine's violet smoke, gold's immutable luster. Each revelation carries narrative weight. Experiments confirm not just existence but character, and in understanding these elements, humanity glimpses the poetry of matter. Each atom becomes a storyteller, each element a character in a cosmic drama that spans space, time, and consciousness. Finally, revelation illuminates the bridge between science and life. Carbon forms the scaffolding of biology. Oxygen fuels respiration. Iron circulates in blood. Silicon underpins technology. The periodic table is not an abstract schema. It is the blueprint of reality. Revelation transforms observation into understanding, showing that atoms are not just substances, but agents in the unfolding story of life and civilization. Revelation is, therefore, a mosaic. Atomic theory, spectroscopy, radioactivity, noble gases, isotopes, synthetic elements, each a piece contributing to the larger image of understanding. The periodic table emerges as both map and narrative, a framework through which humanity interprets matter, space, and time. Each new insight deepens the story, revealing that nature is intelligible, patterned, and profoundly poetic. As Chapter 3 closes, revelation is not an endpoint, but a gateway. The discoveries of the past lay a foundation for the consequences that follow, the applications, impacts, and transformations that elements enable. Revelation illuminates the invisible, deciphers the complex, and inspires the next generation of curiosity. It is the moment when the unknown becomes known, when mystery becomes structure, and when the periodic table transitions from a collection of facts into a living story of cosmic, chemical, and human significance. Revelation alone does not complete the story. Knowledge of the elements, their properties, and their cosmic origins sets the stage, but the true measure of understanding lies in consequence, in the ways these discoveries reshape humanity, life, and civilization. The periodic table is not merely a catalog of matter. It is a blueprint for technological triumph, societal transformation, and philosophical reflection. Consequence is the ripple that flows from insight, touching chemistry, industry, medicine, and even our perception of the universe. The first consequences emerged in the laboratory and the workshop. Sodium, potassium, and calcium, once hidden in compounds, became tools for understanding reactivity. Mercury, arsenic, and phosphorus, substances that had long been objects of fear and alchemical mystery, were isolated, measured, and applied. The experimenters' meticulous observations became practical knowledge, allowing humanity to manipulate matter with precision. Chemistry moved from speculation to application, bridging wonder with utility. Industrial Revolution was the first era where consequences became tangible. The isolation of elements, such as aluminum, transformed industry. Once more valuable than gold, aluminum became light, strong, and malleable, reshaping transportation, architecture, and tools. Iron and steel, refined through knowledge of carbon and metallurgical chemistry, enabled bridges, railways, and skyscrapers. The consequences of elemental understanding extended beyond the laboratory, touching daily life, commerce, and civilization itself. Medicine also felt the consequences profoundly. Iodine, discovered through careful chemical isolation, became a safeguard against goiter. Calcium and phosphorus illuminated the biology of bones. Iron, understood through atomic insight, enabled treatment for anemia. Radioactive elements like radium, cautiously applied, led to new treatments for cancer. Each element carried potential for both healing and harm, demanding responsibility alongside discovery. Consequence is thus intertwined with ethics. Knowledge transforms the world but demands stewardship. Energy, too, is born from elemental understanding. Uranium, plutonium, and thorium emerged from experiments, offering unprecedented power. Nuclear energy revealed the atom as a source of light, heat, and, tragically, destruction. Gravity and cosmic formation may have shaped matter, but human insight harnessed it. The consequences of these discoveries resonate politically, ethically, and philosophically. The periodic table is not static. It is a dynamic framework that mediates power and potential. Consequences also manifest in technology. Silicon, a seemingly mundane element, became the heart of computers, microchips, and modern communication. Rare earth elements power magnets, screens, and batteries, shaping global industries. Gold, copper, and aluminum enable connectivity and infrastructure. Every device, every innovation, rests on the foundation laid by elemental revelation. Consequence is visible in daily life, where atoms orchestrate progress in ways once unimaginable. Exploration of rare and synthetic elements extends the consequences into the future. Technetium, promethium, and super-heavy elements, existing briefly yet precisely measured, challenge understanding of matter and inform nuclear physics. These discoveries push the boundaries of possibility, inviting applications that were inconceivable decades ago. Science becomes both mirror and compass, revealing nature's design while guiding humanity toward new horizons. Consequence is therefore both practical and aspirational, extending from utility to imagination. Society itself is shaped by elements. Gold, silver, and platinum defined wealth, power, and culture. Iron and copper built tools, weapons, and machinery. Carbon's role in coal and hydrocarbons fueled industrial economies. Uranium and plutonium shaped geopolitics. Consequences ripple across human systems, showing that elemental understanding is not abstract but intimately connected to societal structures, economics, and civilization's trajectory. Science and society are intertwined, and each elemental discovery resonates beyond the laboratory. Environment is another canvas for consequence. Understanding elemental cycles, nitrogen, carbon, oxygen, phosphorus, transformed agriculture and ecology. Fertilizers, water treatment, and pollution mitigation rely on knowledge of elemental behavior. Yet consequences are dual. While elements sustain life, misuse or imbalance can devastate ecosystems. Mercury, lead, and arsenic pollution remind us that knowledge carries responsibility. Every revelation in the periodic table has environmental ramifications, teaching that consequence is inseparable from ethics and stewardship. The cosmic perspective amplifies consequence. The same elements forged in stars and supernovae that comprise Earth's crust, oceans, and atmosphere also inform our understanding of planetary formation. Spectroscopic analysis of stars reveals the abundance of hydrogen, helium, carbon, and oxygen, confirming that life's building blocks are universal. The periodic table is not merely terrestrial, it is cosmic. Consequence extends beyond human experience, connecting life on Earth to the broader universe. Understanding elements allows us to trace our origins and anticipate planetary and stellar evolution. Education and culture also bear the mark of consequence. The periodic table is taught in schools worldwide, a symbol of human inquiry and the quest for understanding. Art, literature, and philosophy have drawn inspiration from the elements. The glitter of gold, the glow of radium, the utility of iron. Consequence is cultural as well as scientific, shaping imagination and identity. Humanity interprets matter not only through measurement, but through meaning, connecting chemistry to experience, atoms to narrative. The practical consequences of elemental knowledge are intertwined with human creativity. Materials science, electronics, pharmacology, and energy production all emerge from mastery of the periodic table. Each experiment, each revelation, translates into tools, medicines, and technologies that define civilization. Yet, consequences are neither predictable nor solely beneficial. They require foresight, judgment, and ethical reflection. Knowledge transforms the world, but it also demands responsibility, awareness, and wisdom. Consider the story of carbon. Diamond, graphite, graphene. The same element manifests in diverse forms, each with unique properties and applications. From jewelry to electronics, carbon demonstrates the consequences of atomic arrangement, of human ingenuity in harnessing natural behavior. Each element carries potential, waiting for human insight to channel it into utility. This is the essence of consequence. Understanding leads to transformation, observation to application, potential to reality. The periodic table, once a conceptual framework, now manifests in every aspect of life. Medicine, technology, industry, art, and environment, all are consequences of elemental understanding. Hydrogen fuels stars and rockets. Oxygen sustains life. Silicon powers devices. Uranium shapes global politics. Each consequence is layered, from the molecular to the societal, from the ecological to the cosmic. Human curiosity becomes action, and action transforms reality. Consequences also teach humility. The same elements that sustain life can also destroy it. Radioactive materials, heavy metals, and chemical pollutants illustrate that knowledge carries weight and responsibility. Understanding the periodic table is not merely intellectual, it is ethical. Humanity becomes a steward of elements, accountable for how discovery translates into action. Consequence, therefore, is both a reward and a caution, a reminder of the interconnectedness of science, life, and the cosmos. In conclusion, the chapter of consequence reveals the profound impact of elemental understanding. From laboratories to industries, from medicine to technology, from Earth to stars, the periodic table shapes the world in visible and invisible ways. Human ingenuity, guided by revelation, transforms matter into civilization, life, and culture. Consequences ripple outward, touching every facet of existence, illustrating the power, responsibility, and beauty of knowledge. The periodic table is no longer just a list. It is a blueprint of possibility, a map of influence, and a testament to human curiosity translated into transformation. We stand now at the threshold of reflection, gazing upon the map of elements that humanity has gradually uncovered. Each symbol, each atomic number, represents not just a substance, but a story, a fragment of the universe made intelligible through curiosity, experimentation, and insight. Reflection asks us to pause, to consider not only what we have learned, but how knowledge reshapes our understanding of existence itself. To reflect is to connect. Hydrogen, forged in the first moments of the cosmos, is the same atom that fuels the stars and forms the water flowing through our veins. Carbon, in its simplicity and versatility, binds life into complex structures and, simultaneously, fuels fire and innovation. Iron, once forged in stellar hearts and scattered by supernovae, circulates through our blood and steels our cities. In understanding the elements, we see ourselves in the universe, and the universe in ourselves. Reflection becomes a bridge between science and humanity. Reflection also invites humility. The periodic table, with its order and logic, reveals the elegance of nature's design, yet reminds us of our smallness. We are observers, participants, and stewards of a world far older and vaster than our own lifespans. The elements existed long before us and will endure long after, their cycles of formation, decay, and transformation indifferent to human triumph or error. To understand them is to recognize the delicate balance between knowledge and humility, power and responsibility. Each element embodies duality. Mercury flows like liquid silver, yet is toxic. Uranium can illuminate cities or annihilate them. Carbon forms diamonds of beauty and fuels combustion. These dualities teach reflection. Knowledge is potent, not inherently moral. It is our choices, our intentions, and our foresight that determine whether discovery nurtures life or diminishes it. The elements are mirrors, reflecting both the cosmos and the human heart. Reflection demands that we see these lessons, internalize them, and let them guide our actions. The periodic table is also a testament to perseverance. Reflection reveals the centuries of human curiosity, trial, and insight embedded within each discovery. From the alchemist's humble experiments with lead and mercury to Mendeleev's predictive genius, from the isolation of noble gases to the creation of synthetic elements in particle accelerators, humanity's dialogue with matter is a narrative of persistence and imagination. To reflect is to honor the lineage of inquiry that brought us from mystery to understanding. Through reflection, we perceive the poetic resonance of science. Each atom is a story, each reaction a verse. Sodium ignites water in fiery bursts, iodine colors solutions with haunting violet, and gold shines unchanging through centuries. Experiments, calculations, and observations are not merely technical acts. They are expressions of human wonder. Reflection turns data into narrative, equations into elegy, the periodic table into a cosmic poem. Science, thus, is not devoid of emotion. It is intertwined with awe, beauty, and reverence. Reflection extends beyond Earth. The same elements studied in laboratories are dispersed across galaxies, binding stars, planets, and nebulae. Spectroscopy reveals that sodium, magnesium, and iron shimmer in distant suns. Carbon and oxygen fuel life wherever conditions allow. The universe itself participates in this reflection. It created the elements, and in studying them, we glimpse the grand design of cosmic evolution. Reflection is, therefore, both terrestrial and celestial, connecting our hands to the fabric of the cosmos. Philosophically, reflection uncovers the profound unity of nature. Elements that once seemed isolated are, in fact, interwoven threads in the tapestry of existence. Oxygen supports respiration, carbon constructs proteins, nitrogen fertilizes soil, phosphorus fuels DNA. Understanding these connections elevates knowledge from observation to comprehension, from analysis to wisdom. Reflection illuminates the web of interactions that sustains life, revealing that elements are not solitary entities but participants in a vast network of cause, effect, and interdependence. Reflection also confronts temporality. Elements have stories that span billions of years. Hydrogen from the Big Bang, iron from supernovae, gold scattered across the Earth. Our scientific journey, by contrast, spans centuries. In this perspective, human discovery is fleeting, yet remarkable, a brief flash of awareness within a vast cosmic timeline. Reflection fosters both humility and gratitude. We are transient witnesses to a universe whose complexity far exceeds our understanding, yet we possess the capacity to comprehend, predict, and apply its laws. Ethically, reflection demands responsibility. Knowledge of elements grants power to build, heal, innovate, and, simultaneously, to harm. Radioactive materials offer energy and medicine, yet they also carry the risk of destruction. Understanding mercury, lead, and arsenic informs both industrial progress and environmental caution. Reflection teaches that science is not isolated. It intersects with morality, governance, and stewardship. Consequences ripple outward, and awareness of potential impact is as vital as the discovery itself. Emotionally, reflection evokes wonder and gratitude. The periodic table is more than a scientific tool. It is a map of our origins. We are composed of stardust, atoms forged in ancient stellar furnaces, transformed over eons, and incorporated into our bodies, our world, and our technology. Each element is a reminder that humanity is inseparable from the cosmos. Reflection deepens appreciation for life, for knowledge, and for the intricate processes that connect the microscopic and the cosmic. Reflection also inspires imagination. The patterns and properties of elements suggest possibilities for the future, new materials, energy sources, and medical innovations. Synthetic elements, isotopes, and atomic research hint at discoveries yet to come. The periodic table is not a static archive but a living framework, a source of creative potential. Reflection, therefore, is forward-looking, bridging the awe of understanding with the excitement of future exploration. Finally, reflection unites science and philosophy. The periodic table embodies rationality, observation, and prediction, yet it also evokes awe, narrative, and meaning. It demonstrates that knowledge and emotion, intellect and wonder, analysis and poetry are not opposing forces, but complementary ways of engaging with reality. Reflection transforms the table from a technical reference into a lens through which humanity comprehends its place in the universe, a tool for learning, a mirror for contemplation, and a compass for ethical action. As we close this chapter, the periodic table stands revealed not only as a map of matter, but as a chronicle of curiosity, perseverance, and insight. Reflection reminds us that every element carries a story, cosmic, chemical, and human. Each atom, each discovery, each insight invites awe, responsibility, and philosophical meditation. The journey from unknown to experiment, from revelation to consequence, culminates in reflection, completing the cycle of discovery. In reflection, we see the past and imagine the future. We honor those who uncovered these elemental truths, recognize the impact of their insights, and embrace our role as stewards of knowledge. The periodic table is both a scientific monument and a philosophical mirror, teaching us that to understand matter is to understand ourselves, and that curiosity guided by ethics and wonder is the ultimate legacy of discovery. Reflection, in the end, is a quiet dialogue between human consciousness and the universe. Each element is a voice, every reaction a phrase, and the periodic table a poem, a narrative that spans time, space, and imagination. To engage with it is to participate in the ongoing story of existence, where the fundamental building blocks of the cosmos reveal not only their secrets, but also the profound beauty, order, and mystery of the world we inhabit.